Hello everyone. What you see in front of you today is a particularly interesting little trigonometric identity, and it definitely doesn't look intuitive at first glance. It goes half cosine theta plus a quarter cosine 2 theta plus an eighth of cosine 3 theta all the way to an infinite number of terms, and adding all these up gives you 2 cosine theta minus 1 all over 5 minus 4 cosine theta. This is a rather peculiar identity. It does not seem intuitive at all. It is not elementary. However, there is a way we can actually show that this is true, and to know that, you need to know de Moivre's theorem. So let's write that down. But quickly recall, before we write down de Moivre's theorem, that we can express a complex number z in a trigonometric form, r cosine theta plus I sine theta. And we can also write this in an exponential form, r e I theta. All right? So recall this. Now, de Moivre's theorem states that cosine theta plus I sine theta to the power of n is equals to cosine n theta plus I sine n theta. And if you consider the trigonometric and exponential forms of a complex number, we see that r is equal to 1, so that doesn't change independent of n. And yeah, it follows intuitively because if you raise this to the power of n, then you just multiply the whole thing here by n, and then the theta also gets multiplied by n. An important thing to note about de Moivre's theorem is that it only works for integers. It works for negative integers as well, but it does not work for fractions. So do take note of that when you try to apply de Moivre's theorem. Okay, but how do we use it to solve the problem above? Well, we notice that the real part of cosine theta plus I sine theta is, of course, just cosine theta. So what we're going to do is we're going to let there be a complex number, z. Let z equals to e to the power of I theta. And, of course, equivalently, this is cosine theta plus I sine theta. The left-hand side of the above identity that we're trying to prove can be written as, if you have noticed, we can write this as the real part of z divided by 2 plus the real part of z squared based on de Moivre's theorem divided by 4 plus the real part of z cubed divided by 8, and go on so forth. Now, recall, z cubed is really e to the power of 3I theta, which by de Moivre's theorem, based on this intuitive little result, is cosine 3 theta plus I sine 3 theta. Okay, and the real part of that is, well, cosine 3 theta, and we divide that by 8 to get the term above. So we need to continue doing this. Now, notice that every term is a real number, so what I can actually do is factor out the real part. And notice that everything is also in powers of 2, and we're squaring each of the z terms. So I can actually rewrite this as z over 2 plus z over 2 squared plus z over 2 cubed, and this here is going to an infinite number of terms. Now, what do we see here? This is actually a geometric progression. The first term would be z over 2, and the common ratio is also z over 2. And there is an infinite number of terms. And of course, this is a convergent geometric series because the modulus of z over 2 is half. And therefore, it will become a quarter, an eighth, all the way down to 0. So it's convergent. So we can apply the formula for the sum to infinity of a convergent geometric series. That's going to give you the first term divided by 1 minus the common ratio. So that's the real part of z over 2 over 1 minus z over 2, which I'm just going to rewrite by multiplying the top and bottom by 2. Real part of z divided by 2 minus z. Okay, so what we have here is a complex number divided by another complex number, which is not convenient for us to compute the real part of it. However, what we can do is multiply the denominator, or multiply the top and bottom rather, by the conjugate, because that will make sure that the denominator is a real number. So this is going to be the real part of z times 2 minus the conjugate of z. And then the bottom is going to be divided by 2 minus z and 2 minus z conjugate. And the denominator is now a real number. We can be sure of that. But recall that z is e to the power of I theta. So we're going to rewrite this. So this is going to be e to the power of I theta 2 minus e to the power of negative I theta, because that's how we write the conjugate in terms of the exponential form. And we can rewrite the denominator as 2 minus e to the I theta and 2 minus e to the negative I theta. All right. This here, we can compute the denominator first. This is going to be 4. This is going to be positive 1. And we have 4 minus, we have 5 because 4 plus 1 is 5. 5 minus 2e I theta minus 2e negative I theta. All right, and what's the top going to be? It's going to be the real part of 2e I theta minus 1. All right, let's compute this. The top is just going to be 2 cosine theta minus 1, because the real part of e to the power of I theta is, well, cosine theta. And the bottom can be rewritten as 5 minus 2 times of e to the power of I theta plus e to the power of negative I theta. And if you recall your properties, the identities that we have with the exponential form of complex number, this simplifies quite nicely to 2 cosine theta. So this is 2 cosine theta minus 1 divided by 5 minus 4 cosine theta. And this is exactly the right-hand side if you look back at the top. So this seems very, very unintuitive if you do not know about complex numbers, but I kid you not, this is an identity that will hold true as long as, actually it will hold true for every theta because there's no way that it could be 0. Yeah, so this holds true for every real value of theta. It doesn't look like it, but with a little bit of complex number trickery, we can prove that it actually does. This here is an example application of de Moivre's theorem, and it is one of the easier examples in my opinion. If you're going to like to see more complicated examples of me using de Moivre's theorem to solve problems, then do let me know, and I'll look for some interesting questions. This question in particular has appeared in, I would suppose, quite a number of prelim papers, but the one I had was River Valley High School 2018 prelim, although I feel like this particular question would have appeared a couple of times elsewhere. So do look up de Moivre's theorem and some more of its applications, like finding the roots of trigonometric polynomials and deducing some things about angles. It's really, really interesting. That's it for this video. I hope to talk some more some other time. I'll see you guys real soon.